Very good.
Are you
So,
seeing?
yeah, we can see your
I see
screen.
my.
Thank you. Yep. So it is a great pleasure to introduce our third speaker of the afternoon, Allbens Atman from Belo Horizonte, Minas Gerais. And he's going to talk to us about what can we learn from fluctuations in sheared granular materials. Allbens, thank you very much for coming, for accepting our invitation. It is a great pleasure to have you here. You can please start your talk.
Thank you, Yuri. Good morning, boa tarde, bonsoir. It's a pleasure for me to be here to this great Congress, to very nice talks, and I hope to contribute a little bit with this study about the fluctuation in sheared granular materials. Indeed, what we expect to show to you is a technique to unveil some hiding characteristics that we can usually don't see when we study sheared granular materials. So let me start with this little outline. I will prepare some fundamentals to you to see how the techniques that we use to study the granular materials. Then we pass some phenomenology of the granular materials, granulants, basically, and then the results for the Salis-Buchmann scaling law and the shear bands. Oh, basically, when we have equilibrium in statistical physics, we can study the response of the system due to some excitation that is known the fluctuation dissipation theorem that relies the assumption that the response of the system in thermodynamic equilibrium to a small applied force is the same as the response to a spontaneous fluctuation. So we can build in that way a way to study the linear response and that is typical exponential decay. For example, in the Albert Einstein study in the Brownian motion in his PhD thesis have shown that you can relate the diffusion coefficient to the temperature. So here we intend to study granular materials, but there is a problem that granular materials are out of equilibrium, non-ergodic, and there is no dissipation, fluctuation dissipation relation formally developed. And we cannot apply the assumptions of the central limit theorem. So what we like to show to you that there is a way to study the long-range correlations in granular materials and relate them to the diffusion by the scaling, Salis-Buchmann scaling. So to start, the autocorrelation function for a single grain. And when we have for larger times, we expect that this correlation goes to zero. But for the times going to zero, the distance, the time between the observations, we observe the equipartition theorem. So this is very well known, and we can make the same study for the collective properties of the systems with the stress correlation function that we have a part of the inertial and another part of potential energy, kinetic and potential energy, and we can study the autocorrelation function for the stress, and we have obtained from the kinetic term the momentum transport caused by the atomic motion, and the potential term the same caused by the interatomic forces. And of course, when we have the time between the observations going to zero, we have the shear modulus of the material. Well, from this autocorrelation function, we can obtain the Einstein relations by differentiating them, and also by integrating, we can obtain the Grant-Kubo relations. Basically, we have the transfer by unit area of unit time. The flux is dependent of some coefficient that is related to the resistance to the flow, and some gradient is related to the driving force for the flux. Applying that for a simple one-dimensional diffusion, we have the Fick's law that relates the flux to the diffusion coefficient, and we have the conservation of Mach. Combining these two is very well-known result is the diffusion equation. That's a particular case of the Fokker-Planck equation, and the solution is the very well-known the Gaussian distribution. And if we calculate the second moment of the distribution, we obtain the linear dependence with the time that is very low when this time goes to infinite, the Einstein relation. So, and it is valid when the time of the time is much larger than the time of the atomic collisions, between atomic collisions. Now, if we get the displacement or the time derivative of the displacements and integrate in the both sides, and squaring the both sides and averaging over the time, making changing in the variable, we get this relation that is again the autocorrelation velocity function for the velocity, and recalling the Einstein relation, we can get a formula to calculate the diffusion constant. So now we get a way to recover the Grant-Kubo relations for the diffusion in 3 dimensions, or if we get the stress autocorrelation function, we get the viscosity or the effective viscosity of the system. Now, let's pass to the diffusion. The standard equation of the diffusion is introduced by Fourier in 1822, and we get the solution of the very well-known Gaussians. But and if we calculate the second moment of the displacement, we get the relation of the displacement, the second moment, the variance is proportional to t, the time, to a power alpha. In the case of the normal diffusion, alpha values is equal 1. However, when we have correlation large, we get long-range correlations in the system. This exponent is different to 1. So we get, for example, this is called the anomalous diffusion, and for alpha greater than 1, we have the super diffusive regime, and for alpha lower than 1, we get the subdiffusive regime. And these kind of regimes are observed for granular materials since 2002 by Hajai and Hu. And a mathematical description for this kind of anomalous diffusion can be a generalization of the heat equation that can be a linear equation with fractional derivative that we get as a solution the Levy distribution or the Cauchy-Lorentz distribution, and particularly the Cauchy-Lorentz distribution, we have a super diffusive regime. But we can be another possible generalization of this equation, that is the so-called porous media equation. This is a nonlinear equation, okay? And we have this power to do, generally we know this power as the new exponent, but in fact, Thales showed that we can solve this possible solution for this equation is the q-Gaussian equation, q-Gaussian distribution, sorry. And this q-Gaussian distribution has a parameter. When this q equal 1, we have exactly the Gaussian, but for Q different one, we have either the super diffusive or the sub-diffusive regimes. And then where this power, this new exponent, in fact, can be written as 2 minus Q, where Q is the parameter of the q-Gaussian. Studies also show that it's possible to calculate the second moment using this solution of the q-Gaussian, and we have the second moment for the displacement as the time to the power 2 over 3 minus q. So we have this that is called the Sales-Buchmann scaling law, that alpha, the diffusion exponent, is equal to over 3 minus q. So if we in this equation, in fact, we have two ways to verify that we can calculate directly the diffusion of the particles and obtain the exponent alpha, but also we can calculate the fluctuations and make the distribution, the probability distribution function of the fluctuations, and calculate the Q and verify if there is a direct relation between these two parameters. Indeed, we perform this verification with this apparatus that's called 1 gamma 2 epsilon. Basically, you get here a step motor machine that can control the system. Also, we can control the pressure, and also we can control the shear rate in the system. So I start to rain here. Maybe there is some noise in my talk. And then with this machine, we can perform several tests. For example, the isotropic compression, odometric compression, the axial test, and also the simple shear test, controlling the pressure and the shear rate. Okay. Here is a photo of the experiment. These experiments are conducted in the 3SR laboratory in Grenoble, Alpes University in France. Indeed, I will be there in next February to perform a new analysis with Gael to exactly to understand better. Sorry for that. and here we have this Schnabel rods, okay? That is basically a two-dimensional grains. In this experiment, we have about 12,000 grains, and this is the distribution of size of the grains. We have, in this case, 1, 2, 3, 4, 5 different sizes. And here, a small video to show the experiment, okay, of the shear. You can see the movement of the grains, and in some places we can see that the grains fall in the voids, and this falling implies to large deviations. Okay, so let me. We can take several pictures with a high precision camera, and with the aid of this tracker technique, we can follow each grain with a high precision. And basically have a sub-pixel precision of 0.05 pixel, and calculate at microscopic level the position and rotation of grains. And then macroscopic level, we can have the strain and stress tensor. So I ask you to pay attention that we use not only in this case of this example, we get the picture at the time n, and the picture at the time n+1. And we can calculate the correlation function between all the grains and the displacement field. Basically, as shown here, we have the displacement of each grain, okay? And we have also the stress-strain curve. Please notice that we can perform the calculation of this strain distribution, okay, for different strain windows. This is a very important point, that we vary the strain window. As you can see here, we can have a short, a small window, okay? Here in about, sorry, I can, about 10 to the minus 3, okay? Up to 10 to the minus 1 in values of the strain, okay? So with this, we can variate the strain window and calculate the displacement field and the fluctuations. The fluctuations basically are the difference between the displacement of each grain to the mean affine field imposed by the shear. So calculating this fluctuation, okay, so we can see here the measured displacement measured for each grain and the mean field imposed by the shear. With this, we can do this nice graph that we have the displacement between two images and the fluctuation between the same two images, okay? And now we can variate the window size. When we perform this variation, we observe that the probability distribution function of the fluctuations depends on the strain window. It's not a trivial result, and it was observed by the first time by the Rheology and Roux in 2002. And we can see for the short, very small window, strain window, we have this long-range correlation, this fat tail distribution, as you can see here. I showed to you that one, that is clear. So the black one is obtained when we have a very small window, but when we have a larger window, we have the Gaussian, a Gaussian distribution, probability distribution. So the distribution of the fluctuations depends on the strain window. This is the first result that Rheology and Roux called granulance. It's a new phenomena in granular materials that we have explored first in this powders and grains conference paper. And after, we perform a very detailed study of these fluctuations by two approaches. First, we fixed the strain window in this example to the 10 to the minus 3 and vary the strain, the total strain. So we can see that we have for small strain a long range correlation, and for very large strain we have these short range correlations. But we also can fix the strain in the case we have the strain for all the system, and vary the strain window to calculate the fluctuations. So when we perform this study, varying the window of the strain, we observe these two regimes. And here we have another video to exemplify this. First, we get a difference of 200 images to calculate the fluctuations. And we can see here this black spots that correspond to the grains, and these arrows that corresponds to the fluctuations. Then we can see that the seam is very smooth. Okay, this is a typical result for a Gaussian distribution of the fluctuations, the probability distribution fluctuation. So you can see here as the time, as the strain, as the time passes, the strain increases, and the calculations between 200 images allows us to calculate the probability distribution function. So it's the first case for a very large window, and now the same experiment, exactly the same experiment. It's not another experiment, it's the same one, but now the strain window is only 5 images. So see how different the system behaves. There is a lot of patterns that we cannot observe than when we have a large window strain, okay? And we can observe that for as now, just passed, that sometimes all the system have a fluctuation pattern that is completely different. So the transition is not smooth between the images, okay? It is very not trivial, not expected, okay? And it's caused a lot of surprise for my colleague Gael when I was there in 2012. And even he, in the first paper that he published, he not show these results because he thinks that something was wrong in the analysis. Well, but we decide to perform with this experiment. So we use the Gaussian, the q-Gaussian distribution to perform the fit of the probability distribution function. Here for the two analyses that I showed to you, there is the head one with a small window, and we have a Q of 1.5, more or less, okay? And the short and the large window, the blue one, the blue curve, we have a Q of 1.22. So showing explicitly that the distribution depends on the strain. And we can vary the strain for a wide range of values, and we observe this behavior. We observe this plateau is about 1.5 for the value of Q, and for the short strain, notice that we have here 1 over the square root of the strain window, and for the very large strain, we observe that this curve approaches to 1, exactly as predicted by the Einstein Smolensov equation. That's a Gaussian distribution. Okay, so now we verify that with an independent measure that of the displacement, the mean square displacement of the second moment of the displacement. Sorry, and we measure the exponent diffusion exponent alpha, and we perform this for all the points of the strain windows, and we get this curve. Please notice that this dashed curve line is not a fit. This dashed line is exactly the prediction made utilizing the Salles-Buchmann relation. So this is a very convincing result that we have published in PRL in 2015, and showing that we can, it's important to better understand the nature of the fluctuations in a granular material, shear granular material, to perform a different strain windows to calculate the fluctuations. Okay, oh well, once we have this technique to understand how the fluctuations work in these granular materials, we pass to a step further. We have to decide to investigate shear bands. The shear bands occur in these materials, in these systems. Just a minute. Here. Here. So we have this kind of biaxial test, okay, in the simulations, that we can see these lines of a big strain in the system, okay, that is called shear bands. And these shear bands, let me pass again, okay, are very difficult to predict where they occur and even when these shear bands occur. So we have the hope to use this technique, I call the granulation technique, okay, to study different kind of shear bands and build the distribution function, the probability distribution function for these bands to compare with the usual technique to identify the shear band. The usual technique is exactly to measure the shear, the deformation or the strain along the simulation. Here is the results for the shear. Okay, so we can see that as the shear increases, we can observe these regions of the long-range correlations in the system. Here we have these black lines to indicate the length of the correlation. Okay, and we can perform the traditional percolation threshold to find exactly where is the point of the percolation of the system when the shear bands make all the system to collapse, the resistance to collapse. And this is the typical result. Okay, when we get this the traditional study, and we can observe in these black circles the onset of this shear bands arising in the system. But is a posteriori analysis. Okay, we cannot perform this at the same time that we perform the experiment. Here is our result that we have published in 2018 in Entropy for the same experiment that we comprove the Tsales-Buchmann law. We perform with this example of the shear, where the shear bands appears, and we can observe the same plateau of the small values of the strain window, but the value of the Q is not longer 1.5, is about 1.27, 1.3, the first difference. And another important difference that we observe that this line, which is the predictor of the Tsales-Buchmann scaling law, okay, is the value of the Q diverges from this curve from a given point. And this given point is exactly with the onset of the percolation of the system. So we believe that it's possible to optimize this analysis in order to predict where the shear bands can occur. Okay, and we can see here that the traditional percolation analysis using the percolation length, okay, we observe the giant cluster, the infinite cluster in the percolation exactly in that point that we observe that the value of Q is non-monotonous, non-monotonic. So this is a first result of this analysis, and I expect to, in the next months in Grenoble, to perform another analysis to better understand this behavior, and maybe propose a new technique to identify and quantify shear bands in sheared granular materials. Well, thank you a lot for your attention. This is my collaborators in this work, Vincent Richefort and Gael Comp from the 3SR laboratory in Grenoble. Marta Stasiak is the former PhD student which made the first analysis and data for the Tsales-Buchmann scaling law. And Léo Vialon is the present PhD student, which will perform the current studies. Thank you a lot for the attention, and I'm open to your questions.
Thank you very much, Allbens, for this very nice talk. Do we have any questions? Allbens, I have a quick question. Yes. Well, probably two questions. So when you showed us though that the differences in the fluctuations that you measured on the videos, yes, when you considered 200 images and 5 images, so you were saying that when you measured taking two different sampling frequencies, you got different results. So is
Yes,
there
for
some
the
sort of,
distribution.
yeah, so is there an equivalent of a Nyquist frequency for this, for the analysis of these images, a frequency at which you can say that you have a converged result that will get you what exactly the system is trying to, well, what is exactly the behavior of the system? Or is it not
Yes,
something related to that?
No, I believe this is exactly that one, because when you get this, we get the very short window, very small window, we get this long range correlation, okay? And this is exactly when we can observe that a single displacement of grains, okay? And of course, this single displacement should be correlated, okay, in somehow, okay? But when you get a very large window, the grain have a lot of displacements, a lot of collisions. So you get to the thermodynamic, more or less, it's not thermodynamic, but in the path for the thermodynamic the limit. This is exactly this close to one limit. So what is the real nature of the fluctuation of the system? That is not very clear for me, at least, okay? It depends what you can see in the system. Okay?
I see. All right. And the other question would be, at the very beginning of your talk, you showed some integrals that we could relate the fluctuations of the systems to macroscopic properties, such as viscosity or diffusion coefficient. Yeah, something like, yeah, diffusion coefficient and viscosity. Have you built these viscosities or diffusion coefficients from your fluctuations measurements?
Not yet, okay, but because we need this we need also this potential is very difficult to calculate from experiments, okay? From the simulation we can calculate it, and we have we can do this, we can perform this, but the experiments we don't have this very easily to calculate. What Gael is doing now exactly is to try a way to calibrate the shear cell, okay, to calculate the contact force to each grain. We can perform this calculation, will be possible to obtain this effective viscosity, which will be also another very interesting result to show.
You can eventually get some close to the μ curve somehow, because you have the pressure, you have the shear rate. You just need to see whether you can relate your fluctuations to something that is comparable to the μ. Very nice, Allbens.
Yeah. Thank you.
Do we have any more questions? Okay, so thank you very much, Allbens, for your talk.
Thank you.
Let me stop the recording.